All right, this is the fourth and final video in a series about the precise definition of a limit. In the first video, I talked about the definition of a two-sided limit. In the second video, I went over the definition of one-sided limits, both of them. And in the third video, I talked about limits at infinity and its definition. In this last video, I'm going to talk about infinite limits. Now, before I get into that, we are going to recall first what the two-sided limit definition looks like. Let f of x be defined on an open interval around n. We say that the limit of f of x as x approaches n is the number L. So we are using this notation. If for every epsilon greater than 0, remember epsilon represents a small positive distance, a small positive number, there exists a corresponding number delta greater than 0, another small positive number, such that as long as x minus n is between 0 and delta, we should hope to see that f of x minus L is less than epsilon. Now again, these are distances we are talking about, so we just want to be close to n as our x's and close to L as our y's. Okay. Now, the question again, how does the definition change for infinite limits? Now, infinite limits, hopefully you recall, are limits that go to positive infinity or negative infinity with y values. So, here's the first one. And I'm going to approach it again from the perspective of there's one that goes to positive infinity, there's one that goes to negative infinity. So this is just the positive infinity one. Let f of x be defined on an open interval around n. We say that the limit of f of x as x approaches n is positive infinity if for every m greater than 0, there exists a corresponding number delta greater than 0, such that as long as x minus n is between 0 and delta, we should have f of x values that are bigger than m. Remember, m should represent a positive big number. Now, m and n can be used interchangeably. So if you write n up here, that's okay too. It's not a big deal. What we want to be getting across to our readers is that m is a big number. N is also a big number. That's the important part, is these are capital letters because they're big numbers. All right. Now that I've got that handled, we'll look at a picture of it. So I've got my x interval here from n minus delta to n plus delta, and I want every single thing in this green region to be above m. M is my cutoff. I want all of these answers to be greater than m so that I know it's headed toward positive infinity. Okay? M is representing my cutoff value. Everything should be bigger than m. Now, on the other side, the other kind of infinite limit goes to negative infinity. So let f of x be defined on an open interval around n. We say that the limit of f of x as x approaches n is negative infinity. Notice the negative infinity there. If for every n less than 0, there exists a corresponding number delta greater than 0, such that our x minus n is between 0 and delta means that f of x should be less than n. We want really big numbers that are negative. So, negative 100, negative 1000. We want to choose numbers as a cutoff that are negative. Okay. So visually, here we go. I had to choose a really small interval here, n minus delta and n plus delta, so that all of these answers ended up way down here at the bottom, past this cutoff of n. Again, n is my big negative number in this case. And I want to make sure everything there is in that blue region down here at the bottom. That's my goal, is make sure all those answers are down there. As we go through, I want to remind you again to think about this. Since y is approaching infinity, we want to think about m or n as a cutoff. It's, the bare minimum. Anything beyond m is what we want, or anything below n is what we want. As we get closer to that desired x value, the y value should pass that m or n boundary. We want to also continue with a recap. All infinite limits end the same way. Notice if I go back and look at those infinite limit definitions, they end in very similar ways. If it's ending in negative infinity, it needs to end with something like that at the end, f of x less than n. If it's got a positive infinity, it should say f of x is greater than m. We want that kind of part in our definition. Pay attention to the variables defined. M and n are pretty much interchangeable. Just be careful which one is being used in that definition. Infinite limits are when the y is unbounded. Limits at infinity are when x is unbounded. Remember, limits at infinity were the focus of our third video. Infinite limits are the focus of this video. Lastly, it's important to notice that depending on what our y value approaches, it alters the second part of our definition. And these can be broadly categorized as a numerical limit using L. We have the absolute value of f of x minus L is less than epsilon. Or we have an infinite limit. If it's going to positive infinity, we said that f of x is greater than whatever that positive number is. If we're going to negative infinity, it's f of x is less than whatever that negative number is. And that's the important part with this video. Hopefully this helps you guys figure all this out, and hopefully everyone will have a great day. Bye.